The treatment room at Kenstone Regional Oncology Center was quiet, except for the low hum of the machine. It was June 1985, and the Therac-25 represented the cutting edge of cancer treatment technology, a computer-controlled linear accelerator that could deliver precise doses of radiation to tumors while sparing healthy tissue. Sarah, a radiation therapist with 5 years of experience, had been working with the Therac-25 for several months. The machine was different from the older models she'd trained on. Everything was controlled by computer now, no mechanical interlocks, no redundant safety systems that clicked into place. Just a keyboard, a screen, and the software's assurance that everything was properly configured. She positioned her patient, a woman in her mid-50s receiving treatment for a tumor. The routine was familiar. Enter the patient data, select the treatment mode, electron beam for surface treatments, X-ray mode for deeper tumors. The Therac-25 could switch between them automatically, rotating different components into the beam path. Today's treatment called for X-ray mode. Sarah typed the prescription parameters into the computer terminal in the control room. The machine responded with its usual displays confirming the settings. She pressed the B key to begin the beam. The screen flashed malfunction 54. The dose display showed a reading far lower than prescribed. Sarah had seen this error before. The manufacturer's manual said it was a common glitch, nothing serious. The protocol was clear: reset and retry. She pressed P to proceed, resetting the machine. The display cleared. Everything looked normal. She pressed B again. The intercom crackled immediately. The patient's voice was tight with pain. "Something's wrong. It feels like I'm burning." Sarah looked at the display. It showed normal readings. The dose delivered was what had been prescribed for the session, but the patient was in distress. She rushed into the treatment room. The woman was clutching her chest, her face contorted. "It felt like someone put a blowtorch on me," she said. There was no visible injury, no burns on the skin. The treatment had lasted only seconds, but something had happened. Over the next weeks, the patient's condition deteriorated. The pain intensified. What began as an invisible injury manifested as tissue damage far more severe than her prescribed dose could have caused. She died 5 months later. In Tyler, Texas, another therapist encountered the same malfunction 54 error during a treatment in March 1986. Following the manual's guidance, he reset and continued. The patient reported an intense burning sensation. Within days, red marks appeared on his skin. Within months, he was dead from radiation-induced complications. At Yakima Valley Memorial Hospital in January 1987, the pattern repeated. The error appeared. The operator followed procedure. The patient felt searing heat. This time, witnesses in the control room noticed something on the display. A fleeting moment where the dosimeter reading spiked before settling to what looked like a normal value. But by then, the patient had already received what investigators would later estimate to be 16,500 to 25,000 rads, roughly 100 times the prescribed dose. He died 3 weeks later. For the therapists, the horror was compounded by helplessness. They had followed the manual. They had trusted the computer's displays. The machine showed normal readings, normal doses delivered, yet their patients were dying from radiation injuries that shouldn't have been possible. When therapists reported the incidents to Atomic Energy of Canada Limited, the Therac-25's manufacturer, they were told the overdoses were impossible. The computer wouldn't allow it. The software had built-in safety checks. The machine was designed so that such errors couldn't occur. But the injuries were real. Patients developed radiation burns in patterns that matched the treatment fields. Some lost the ability to use their arms. Others experienced neurological damage. The pain was described as unbearable, electric shocks, burning sensations that wouldn't stop. Hospital physicists began investigating. They attempted to recreate the conditions that led to the overdoses, pressing keys in the same sequences the operators had used. Most of the time, nothing unusual happened, but occasionally, Very occasionally, when the treatment mode was changed rapidly, when specific timing conditions were met, the machine would deliver the raw, unfiltered electron beam at full power while reporting a normal dose. The race condition in the software created a window of vulnerability. The computer would command the beam to fire before verifying that the proper filtering and scattering components had rotated into place. For a fraction of a second, patients were exposed to the unattenuated beam, a concentrated dose of radiation equivalent to standing in front of an industrial X-ray machine. Families waited as their loved ones deteriorated. There was no treatment for acute radiation syndrome at these levels. Doctors could only manage pain and watch as tissue broke down, as organs failed, as the invisible damage became devastatingly visible. The survivors bore permanent injuries. Vernon Kidd, treated in Tyler, experienced partial paralysis and chronic pain for the rest of his life. Others lost function in limbs, developed persistent neurological problems, or lived with the fear that the radiation might trigger cancer years later. By the time regulators ordered all Therac-25 machines shut down in 1987, at least 6 people had been catastrophically overexposed. 3 had died. The others would carry the consequences for the rest of their lives. The Therac-25 accidents represent one of the most significant medical device failures in history. The deaths and injuries were not the result of random chance or unforeseeable circumstances. They emerged from specific, identifiable flaws in design, testing, and oversight, flaws that only became clear after people had already been harmed. What follows is not an attempt to relive those terrible moments, but to understand what went wrong and why. The goal is not to assign moral blame to individuals who acted in good faith, but to examine the systems, assumptions, and decisions that made these tragedies possible. In that examination lies the possibility of preventing similar failures in the future, and ensuring that those who were harmed are remembered not just as victims, but as the reason we demand better. At its core, the Therac-25 failure was a software concurrency error, a race condition that allowed the machine to fire the electron beam before safety-critical components had moved into position. To understand how this happened, we need to understand what the Therac-25 was supposed to do. The machine could operate in 2 modes: electron beam mode, a relatively low-energy beam for treating surface tumors. The beam was scattered and shaped to spread the dose over a treatment area. X-ray mode, for deeper tumors. The electron beam struck a tungsten target, producing X-rays. A flattening filter spread these X-rays evenly across the treatment field. Between these modes, a turntable mechanism had to rotate. In X-ray mode, the tungsten target and flattening filter had to be in the beam path. In electron mode, these components had to be out of the way. The Therac-25's predecessors, the Therac-6 and Therac-20, used mechanical interlocks. Physical switches confirmed that the turntable was in the correct position before the beam could fire. If the target wasn't in place, the machine couldn't activate. The Therac-25 eliminated these mechanical safeguards. Everything was controlled by software. The computer tracked the turntable position through variables in memory. If those variables indicated the correct position, the software allowed the beam to fire. The race condition occurred when operators edited the treatment parameters too quickly. Here's the sequence. An operator would enter data for one mode, say electron beam therapy, then realizing they needed X-ray mode instead, they would quickly cursor back up and change the mode selection. If this happened within about 8 seconds before the turntable had time to complete its rotation, the software would sometimes get confused. The display would show X-ray mode. The operator would believe the machine was configured correctly, but internally a flag controlling the turntable position hadn't updated. The software thought the machine was still in electron mode. When the operator pressed the beam on button, the Therac-25 fired the full power electron beam directly at the patient, without the tungsten target to convert it to X-rays, without the scattering and flattening components to spread it safely. The result was a concentrated dose of radiation. Estimates ranged from 16,500 to 25,000 rads, compared to the intended 200. It happened in less than a second. The malfunction 54 error operators saw was a cryptic message triggered by an unrelated safety check, an overflow in a dose monitoring counter. But the error message gave no indication of what had actually gone wrong. The manual described it as a routine fault that should be cleared and ignored. Worse, the dose display showed the prescribed dose, not the delivered dose. Even after a massive overdose, the screen told the operator that everything was fine. This was not a single bug, it was a constellation of design failures. The race condition that allowed beam activation before the turntable was positioned, the absence of independent hardware interlocks that would physically prevent the beam from firing in an unsafe configuration, the cryptic and misleading error messages that obscured the severity of the fault, the decision to display prescribed dose rather than actual delivered dose, the removal of mechanical safety systems without compensating software rigor. Each of these alone might have been survivable. Together, they created a system that could harm patients while assuring operators that nothing was wrong. Understanding these technical failures is essential, but they don't explain why the flaws weren't caught before people were injured. That requires looking at how the system was developed, tested, and regulated. Software treated as infallible. The manufacturer believed that software-based safety systems were inherently superior to mechanical interlocks. This belief was not supported by rigorous verification. The code was not formally reviewed, there was no systematic hazard analysis asking, what if the software fails? Inadequate testing. The race condition only manifested under specific narrow timing conditions, when an operator edited parameters too quickly, within a narrow window. Standard testing procedures didn't explore these edge cases. The software was reused from earlier models without validation that it would work correctly in the new architecture. Poor incident response. When hospitals first reported overdoses, the manufacturer initially dismissed them as impossible. Valuable time was lost while evidence accumulated. Even after acknowledging problems, the company's fixes were incremental, addressing symptoms rather than fundamental design flaws. Regulatory gaps. At the time, medical device software was not subject to the same scrutiny as hardware components. There were no specific standards for safety-critical software in medical devices. The FDA's review focused on radiation safety from a physics perspective, not software reliability. These organizational and regulatory failures created an environment where critical flaws could remain hidden until they caused harm. The physical failure, the uncontrolled beam, was enabled by a system that had placed too much trust in unverified software and too little emphasis on defense in depth. The Therac-25 accidents fundamentally changed how engineers and regulators think about safety-critical software. The lessons extend far beyond radiation therapy machines. They apply to any system where software failures can cause physical harm. Technical lessons. Software is not inherently safe. The Therac-25's designers eliminated mechanical interlocks based on confidence in software control. This was a category error. Software can fail in ways that hardware cannot. Race conditions, overflow errors, unexpected state combinations. Safety-critical systems need layers of protection that don't all depend on correct software execution. 2. Testing cannot prove the absence of bugs. The race condition in the Therac-25 occurred only under specific, narrow timing conditions. Standard testing didn't find it because standard testing doesn't explore all possible states and sequences. For safety-critical systems, formal verification methods, mathematical proofs of correctness, and systematic hazard analysis are necessary. 3. Error messages must be meaningful. Malfunction 54 told operators nothing about what was wrong or how serious it was. In safety-critical systems, error reporting must be clear, specific, and prioritized by severity. An operator should never have to consult a manual to determine if a message indicates immediate danger. 4. Displays must reflect reality, not intent. The Therac-25 showed operators the prescribed dose, not the delivered dose. This design choice made it impossible to detect overdoses. Monitoring systems must measure actual outcomes, not just commanded actions. Human and systems lessons. 1. Trust but verify. The operators trusted the computer's displays and followed the manual's guidance. They had no reason not to. But complex systems need mechanisms for independent verification, ways to confirm that what the system reports matches what is actually happening. 2. Incident reports must be taken seriously. When hospitals reported impossible overdoses, the manufacturer's initial response was denial. This delayed investigation and allowed more people to be harmed. Organizations must have processes for rapidly investigating and learning from anomalous events, especially when those events contradict design assumptions. 3. Complexity hides failure modes. The Therac-25 was more complex than its predecessors, with more software control and fewer hardware interlocks. This complexity created failure modes that weren't obvious and weren't caught by traditional safety analysis. As systems become more automated and software dependent, safety analysis must evolve to address emergent risks. 4. Reuse requires revalidation. The Therac-25 software was adapted from earlier models, but the new machine's architecture was different. It lacked the hardware interlocks that had provided backup safety in the older designs. Reusing code in a new context requires validating that the safety assumptions still hold. Why these lessons still matter? The Therac-25 accidents happened in the mid-1980s, but software-controlled medical devices are vastly more common today. Insulin pumps, implantable defibrillators, surgical robots, and radiation therapy systems all depend on software to function safely. The principles of defense in depth, rigorous verification, and meaningful error reporting are more critical now than ever. Beyond medical devices, these lessons apply to autonomous vehicles, aviation systems, industrial control systems, and any domain where software mediates between human operators and physical consequences. The Therac-25 demonstrated that software failures are not abstract. They cause real injuries and deaths. The people harmed by the Therac-25 paid the price for assumptions that turned out to be wrong. Learning from those mistakes and applying those lessons rigorously is how we honor their suffering and work to prevent it from happening again. In the wake of the Therac-25 accidents, multiple changes were implemented to prevent similar failures. Regulatory changes. The FDA and international regulatory bodies developed specific requirements for medical device software. These include software validation requirements. Medical device software must undergo rigorous testing and documentation. Manufacturers must demonstrate that safety-critical functions work correctly under all foreseeable conditions. Hazard analysis mandates. Before a device can be approved, manufacturers must systematically identify potential failure modes and demonstrate that adequate safeguards exist. Software failures must be considered as part of this analysis. Independent safety systems. Regulations now typically require that safety-critical functions have independent verification mechanisms, hardware interlocks, or redundant monitoring systems that don't depend on the same software that controls the device. Incident reporting improvements. Medical device adverse event reporting systems were strengthened. Manufacturers are required to investigate and report incidents more promptly. Regulators have better tools to detect patterns across multiple reports. Technical and design changes. Modern linear accelerators incorporate multiple layers of protection. Hardware interlocks, physical switches, and sensors verify that beam-shaping components are correctly positioned before the beam can fire. These operate independently of the control software. Redundant monitoring. Multiple independent dosimeters measure the delivered radiation. If readings don't match expected values, the beam automatically shuts off. Clearer interfaces. Error messages are specific and actionable. Displays show both commanded and measured values, making discrepancies immediately visible. Software engineering practices. Development of safety-critical medical software now typically includes formal code reviews, static analysis tools to detect potential race conditions and overflow errors, and extensive edge case testing. Cultural and professional changes. The Therac-25 case is now a standard part of software and engineering and medical physics education. It serves as a cautionary example of what happens when safety-critical systems are designed without adequate verification and defense in depth. Professional societies developed standards and best practices for safety-critical software. The principles of redundancy, independence, and formal verification are now widely accepted in industries where software failures can cause physical harm. Remaining risks and modern relevance. While modern systems are far more robust than the Therac-25, software-controlled medical devices continue to pose risks. The fundamental challenges remain. Software complexity continues to increase, creating new potential failure modes. Network connectivity introduces cybersecurity risks. Medical devices can potentially be compromised remotely. Machine learning and artificial intelligence in medical devices create new challenges for validation and verification. Economic pressures to reduce costs and accelerate development can conflict with thorough safety validation. The Therac-25 reminds us that safety is not automatic. It must be designed in, verified rigorously, and defended through multiple independent layers. As medical technology becomes more complex and software-dependent, these principles become more important, not less. The improvements made since the 1980s represent real progress, but vigilance cannot be relaxed. Each new generation of technology brings new risks that must be systematically identified and addressed. The Therac-25 accidents took the lives of at least 3 people and caused serious, permanent injuries to at least 3 others. Behind those numbers were individuals, patients who came to medical facilities seeking treatment for cancer, who trusted that the technology designed to help them was safe. Their names are part of the public record: Kenneth Hinson, Ray Cox, Vernon Kidd. Others who were injured chose to remain unnamed in public accounts, but their suffering was no less real. Each had families who watched helplessly as radiation injuries took their toll. Each left behind people who loved them and who still carry the loss. The therapists who operated the Therac-25 also bore a burden: the knowledge that following the manual, trusting the displays, doing exactly what they'd been trained to do, had resulted in catastrophic harm to their patients. They were not at fault. They were caught in a system designed in a way that made such failures possible. What happened with the Therac-25 was preventable. The technical flaws were identifiable. The need for redundant safety systems was knowable. The risks of unverified software controlling life-critical systems were, in retrospect, obvious. But in 1985, software was still new enough, trust in automation was high enough, and regulatory frameworks were incomplete enough that these machines were deployed and used in good faith. The people who died and were injured paid the price for lessons that had not yet been learned. The changes that followed, stricter software validation, mandatory hardware interlocks, better incident reporting, clearer error messaging, exist because of what happened to those patients. Every modern linear accelerator that safely delivers radiation therapy, every medical device that undergoes rigorous software testing, carries forward the lessons written in their suffering. This is not redemption. The people harmed by the Therac-25 do not get their lives back. Their families do not get their grief undone. But their experience became knowledge, and that knowledge has made medicine safer for everyone who has been treated since. The responsibility we carry forward is to never forget that behind every technical lesson, behind every improved standard, behind every regulatory requirement are real people who trusted systems that failed them. Our obligation is to learn those lessons thoroughly, apply them rigorously, and remember that the stakes are always human lives. The Therac-25 cannot be undone, but the determination to prevent such failures in the future, to question assumptions, to verify rigorously, to demand defense in depth, to take incident reports seriously, can honor those who were harmed by ensuring that their suffering was not meaningless. In remembering them, we commit to doing better. That is not enough, but it is what we have to offer, and it is what we owe them.